All right, we're going to talk about molecular polarity. And when a polar molecule is placed in a magnetic field, molecules align with the field. So here we have these electric plates turned off. Here on the right-hand side, we have one positively charged, one negatively charged plate, and the negative ends of the molecule align with the positively charged plate, and the positively charged ends of the molecule align with the negatively charged plate. So a molecule like HCl will arrange in this way. Probably familiar with the idea of polarity. You often will hear that acetone is a polar solvent, and that's how we use it very often, is to think about solubility. Uh, a molecule has a dipole moment, and that's what's actually measured by this experiment. Peter Debye came up with this way to determine whether or not a molecule was polar, as well as to the magnitude of its polarity. So let's look at a simple diatomic molecule here first. We have HI, and we very naively, when we draw our Lewis structure, put a line here, and we imply that these electrons are shared when we're doing coming up with the Lewis structure and doing our Lewis structure counts. But in fact, the two electrons that occupy the bond are much more on the iodine than they are on the hydrogen, because we have a difference in electronegativity. The iodine is better at stabilizing the electron, so electrons get polarized toward the iodine. And so we have a separation of charge in this molecule with a small negative charge on the iodine and a small positive charge on the hydrogen. These little deltas are to remind you these are very, very small. This is not a minus 1 and a plus 1, but in fact this is something really small. Maybe a minus 0.1 and a plus 0.1, or maybe even smaller than that. Just very small charges on them. But the small charge is enough with a separation of charge to create a dipole, which can be measured. Here's the whole periodic table. I'll remind you that fluorine has the highest electronegativity, and the other one, the only one that's very weird is hydrogen. Hydrogen belongs here in the periodic table, but for the purposes of assigning relative electronegativity, it lies somewhere between boron and carbon, so it might be better to put it right there in terms of electronegativity properties. All right, and this is the way that we show dipole, is to show the dipole moment using this arrow. So I have an arrow that points always from the positive charge to the negative charge. And we indicate that by drawing a regular arrow, but then putting a hash across on the positive side. So this looks like a positive is one way to remember it, and it points from the positive atom to the negative atom. We usually draw them next to them because it's just difficult to see if we were to draw it all on top of each other. It always points toward the more electronegative atom. And here's HF, where we have a even bigger difference in electronegativity. And this is a model of the electron density. The red or orangish colors being more negative, and the bluish colors being more positive. So what's happened in this molecule is the hydrogen in HF has less electron density than a hydrogen atom, and the fluorine in HF has more electron density than a fluorine atom. And so that's what we're seeing here. The two electrons in the covalent bond are much more strongly attracted to the fluorine than the hydrogen. Again, not being a full minus 1 and plus 1, but being a pretty substantial charge in the case of HF. Okay, so this HF is a dipole. Okay, and then let's contrast that with diatomics of the same element. Okay, they have no permanent dipole moment and are nonpolar molecules, and it can even be two atoms that have a really high electronegativity, but these two have exactly the same because this is a homonuclear diatomic. And so since they're identical twins, and if this is a tug of war for the electrons in the bond, they're equally strong, and so we get, for our electron distribution, we get this symmetric distribution of the electrons. Okay, versus when we have different elements we get a distribution that makes the molecule polar, because there is a positive end and a negative end for a diatomic of two different elements. All right, here it gets interesting now. So molecules with 3 or more atoms, it depends on the polarity of the bonds plus the geometry of the molecule. So CO2, for example, has 2 very polar bonds. This bond is very polar, this bond is very polar. But the polarity is equal and opposite. So the dipole to the left perfectly cancels the dipole to the right because of the shape of the molecule. So there's no net dipole moment, and therefore CO2 is nonpolar. Its electron distribution, so as promised, the 2 bonds are very polar. So it's very blue in the middle, very orange and red on the oxygen over here, but it's equally red here. And so this molecule has a symmetric electron distribution. If we were to cut here, electron distribution is mirrored. If we were to cut through the atoms, it's mirrored. So it's a very symmetric electron distribution. All right, so same deal, 3 atoms, but this time arrange them to form water. Now we have again 2 very polar bonds, but we have a little bit different situation. So both of them point inward toward oxygen, but they point up and in. Okay, this one points to the right and up, this one points to the left and up. And so the right-left portion of this dipole cancels, but the up portion, there's nothing to cancel it. And so we're left with an up dipole here. This bent molecule, we're left with a net dipole. And check out its electron distribution. It has a defined positive end. This is our hydrogens down here, and this red-orange end is our oxygen atom. Oxygen, and then our 2 hydrogens. So to summarize these 2, no net dipole, even though we have 2 very polar bonds. A net dipole with 2 very polar bonds. Okay, in general, this doesn't work every time, but it works almost every time. If you have a lone pair on the central atom, it almost always is a polar molecule. So ammonia, NH3, is a polar molecule. And again, check this out. Very red up here. This red, this is our lone pair of electrons up here at the top, very red. And then the blue on the bottom is from our hydrogen atoms. And the lone pair creates a dipole with a negative end up here. Here's another example. So carbon tetrachloride, each CCl bond is very polar. However, due to their structure, all of the individual dipoles cancel out. And here's a good way to visualize a tetrahedral structure for this purpose, is you can inscribe it inside of a cube. And so we would have our carbon here in the center of the cube. These 2 top corners would be chlorine. These 2 bottom corners would be chlorine. And so if we do all of our work here, we get a net dipole up from these 3 atoms, and then we get a net dipole down from those 3 atoms. So the up and down cancel each other out, and so this has no net dipole. All right, here's a few for us to compare now. Determine whether the following molecules are polar. BF3. So it has 3 very strong individual dipoles in it. However, they're all equal and opposite, and so they cancel each other out to give us no net dipole. If we take the same general structure, this is a carbon in the middle, this is a chlorine, this is a chlorine, this is a double bond oxygen here at the top. Well, since these are not identical atoms, we end up with a net dipole at the end. With NH3 here, we have 3 very polar bonds, and all of those dipoles point at the nitrogen. So some portion of the dipoles cancel out. However, they all point in an upward directions, and so we get a net up dipole at the end. If one position is occupied by a lone pair or they're different terminal atoms, the molecule will be polar.